Okay, I think we've managed the impossible. We've actually switched it over. Okay, excellent. Okay, so it's my pleasure to introduce Daniel. I think everyone in this call knows Daniel. So, Daniel, we've 20 minutes. Let's have a look. Yes, 20 minutes, and we can have a few questions at the end, which I'll facilitate.
Yeah,
Uh,
yeah,
talk about the role of haptics in collaborative robot applications.
yeah. I'd love to. Thanks for that introduction, John. Hi everyone. Yeah, most of you might know me as Daniel. So I'm just gonna get into this. Um, let's start with a scenario. Imagine you're a technician at a mine site servicing an excavator um, that's losing money almost every minute it's in the workshop. The maintenance task is to remove a bushing from a bearing that's been jammed after months of wear. If everything is rated correctly, traditionally you would set up a hydraulic ram and with the force of half a stick of dynamite, yank the bushing out. But what happens when that's not the case? Let's start by looking at our first case study. So in many industrial environments, especially those involving heavy machinery such as hydraulic systems, maintaining operator safety is paramount. However, the safety measures put in place to protect the operators can also create challenges by insulating them from critical source of information. This has been a problem that's been highlighted for a while now and mentioned in the seminal work of Professor Donald Norman, the problem with automation. As you can see on this slide, he reasons that when implementing automation, not having appropriate feedback for operators puts them at a risk. This is especially problematic in applications like installation and removal of bushings in mining equipment where precise force control is essential. Additionally, operators are often physically separated from the machinery to avoid harm. This insulation, while necessary for safety, limits the operator's ability to perceive vital information about the machine's operation. Traditional feedback mechanisms, such as low-resolution pressure gauges, visual observation of equipment, or auditory cues like unusual noises, are imprecise and unreliable. They can leave operators with limited understanding of system behavior, increasing the risk of accidents and operational errors. So we approached this issue by figuring out how operators were going around this problem. So this is an example of a bushing removal setup. Um, so one interesting approach that popped up was the operators were feathering the on and off switch. Unfortunately, this approach was extremely faulty as it was based on an inaccurate assumption about the system. Operators often uh, avoided doing the math for figuring out the correct tonnage, and as Dr. Norman referred to as utilized procedural reasoning for a task and assumed that simply tapping the on and off switch led to a linear increase in the force applied. This was not the case, as pressure buildup from the hydraulic pump in fact led to a potentially lethal exponential increase in force. But this insight connected to some prior work I'd done using haptics for force feedback in surgery. What if we could enable operators to gauge the pressure in the system using haptics as well? While there were a variety of haptic controllers on the market, the only one that offered a novel adaptive trigger was a DualSense 5 controller. With an adaptive trigger was able to vary the stiffness of the button. It was very able to vary the stiffness of the button press for the user based on the system's output. In theory, this would have allowed users to more intuitively gauge how much force they were applying to the system. So my team developed a simulation based on the equipment available on the site for simulated bearing removal. Our pilot study had roughly 10 participants, and we gained some fruitful insights into this avenue. While on the surface, the results aren't quite as glamorous, most users performed much better with visual feedback like a gauge or even the onboard rumble to guide their performance. It turns out that users felt more confident about how they operated the simulation with the adaptive trigger feedback based on the NASA TLX survey. So this shines light on how such a device could help reduce the cognitive load of operators when used in conjunction with other forms of feedback. Moving to another case study, this one shines a light on another avenue for haptics. We looked that was teleoperation for industrial robots. As you may know, the general overview of the issue is that teleoperated robotic systems, such as the UR3, have become increasingly important in industrial environments where direct human intervention is either dangerous or impractical. However, a significant challenge arises when operators are required to control the systems remotely without the benefit of direct physical interaction. This disconnect can lead to difficulties in manipulating objects precisely, especially in complex or delicate environments. Traditional control methods for teleoperated systems typically rely on visual feedback through cameras or screen displays. While visual cues are useful, they often lack the depth and immediacy required for fine motor tasks, particularly in obstructed or fragile environments where tactile sensitivity is crucial. This creates a gap in operator performance, leading to higher risks of error, increased task completion time, and a reliance on trial and error when positioning or manipulating objects. The lack of real-time force feedback exacerbates the problem. Without an ability to feel the forces acting on the end effector, operators struggle to gauge how much force is being applied, which can result in unintended collisions, damaged objects, or incorrect task execution. This is particularly acute in industries like mining, manufacturing, and remote maintenance, where precision is essential. Applying this to a specific use case of mining robots for rock scaling, and abstracting into our lab, our haptic feedback using a Novant Falcon haptic controller was integrated into a VR-operated UR3 robotic manipulator. This was designed to allow operators to feel the forces experienced by the end effector when simulating tasks like pick and place, push around, or navigate gaps. This feedback mechanism provides a physical connection between the operator and the machine, simulating the sensation of touch and resistance. The core concept here relies on kinesthetic feedback, the sensation of movement and force in the muscles and joints. By incorporating this into the control system, the operator can detect the amount of force being applied by the end effector, allowing for precise adjustments. For example, when the robot arm encounters an obstacle or grips an object, the haptic controller resists the user's input, simulating the feeling of contact or force. Here's a video from our demo showcasing a user operating the UR3. So in this task, the haptic controller is a simple pick and place task. The user is controlling the path of the UR3E as it navigates towards the objects, in this case, the balls, and the various displays assist them in making sure the objects don't roll away. This is to set a baseline for the study and evaluate individual participants' dexterity at the tasks. So as you can see, the robot. So the user using the haptic controller is able to collect the balls, but then it then automatically pastes them where they need to be placed. Yep. I think that roughly gives you the idea of what's going on. So interestingly, the results from the user study showed that haptic feedback increased task completion times and improved overall task accuracy. However, despite the longer task duration, the inclusion of haptic feedback led to a significant reduction in collision rates, indicating that users were more cautious and more precise in their movements. This finding highlights a trade-off between speed and precision when haptic cues were introduced. Additionally, while participants reported higher cognitive workload scores when using haptic feedback, they also felt more confident in their control of the manipulator, suggesting that haptic feedback provided valuable situational awareness. The combination of haptics and visuals demonstrated the potential for a more immersive and reliable control experience, albeit with some impact on efficiency. During testing, operators reported feeling more connected to the robotic system, leading to a more precise task completion. Here, the participants were required to pick up the Rubik's Cube without any collisions in particular. Force feedback allowed operators to make fine-tune adjustments to the end effector positions and force application, reducing the likelihood of errors, such as object collision or joint misalignment. For example, when using the controller, operators often were able to grip and move delicate objects obstacles without through obstacles to avoid, as seen in study 1 and study 2. So in summary, haptic feedback is proving to be a powerful tool in bridging the gap between operators and machines, particularly in complex, high-stakes industrial environments. As we've seen in the case studies, haptics can offer operators a more intuitive connection to the systems they work with, enabling them to feel their way through tasks that would otherwise rely on indirect or imprecise feedback. However, setting up effective haptic interfaces requires a careful consideration because it's not just about adding a haptic element, it's about understanding the context in which it'll be used. Questions around supplementary feedback, such as visual or auditory cues, and the operator's familiarity with the interface are critical in determining the effectiveness of a haptic solution. These factors can significantly impact both the usability and the cognitive load on operators, shaping their overall experience. I'm excited to see how other engineers will explore and expand upon this technology, whether you're interested in it from a UX perspective or an engineering perspective. I encourage you all to see how haptics would play a bigger role in your projects and any other forward collaborations or discussions that might come from this. Thanks.
Thanks, Danielle. All right, we've definitely got time for some questions. Let me see if I can see who's who. Anyone got some questions they want to start with?
Yeah, good question. Interesting talk. Did users kind of comment on like the unnaturalness of like demonstrating tasks using like these kind of like proxy like teleoperation mechanisms, or do you have any comments on that?
Yeah, I think that's a great point. It's the result from the Falcon controller. It was a bit more natural because it was almost like when you were operating it, you almost like felt you were like pushing through things. So the kinesthetic feedback was more like native to how we operate things. But operating something like an adaptive trigger, we found that it was quite cumbersome or challenging to like see how like users are relating like the force buildup to actually how much stresses or how much harder they have to push on the trigger, right? So they have to be able to correlate that. So I reckon either reevaluating how we approach like giving users this controller or like having them do certain tasks before they're introduced to like actually operating a machine or a simulated machine could be like a significant factor in like how people like eventually go on using this.
Yeah, cool. Thanks.
Thanks.
Who's next? Any other questions? I'll ask one then. Are there any studies about using, not because your haptic feedback is about, I guess, the, I don't know, force and things like that. What about temperature and pain? Right? Is that
right?
Has that ever been explored?
So are you actually asking about giving the user like a temperature as a form of feedback?
Yes,
or
yeah. That's
okay.
Particularly in their hands. I mean, that's sort of, it is a type of haptic feedback, as is pain.
I agree.
I mean, you have touch sensors in your hands. You also have pain receptors, right?
Receptors.
I don't know when they kick in. Like, is too much pain. But has that been explored much?
So the papers that I were reading were like exploring different forms of haptics actually started off from like a psychological neuroscience space. So
cool.
like exploring like what makes people uncomfortable or what makes people aware to different stimuli in their environment. And so at the moment they were actually exploring like what constitutes as a pain threshold and if it's even ethical to actually provide
Yeah,
users
of
with
course.
space, right? I think a more safer or more ethical approach would obviously be through temperature. There are certain devices that are so I think the next generation of the DualSense controllers will actually have like temperature-based feedback.
Cool.
So it's gonna get cooler or warmer.
Right.
Yeah. So I'm looking forward to this space, see how it goes. Yeah.
Very good. Okay, excellent. All right. Any quick last questions? Otherwise, we'll move on.
Hello, everyone. Welcome to our presentation. We're going to talk about our translation project 3.5 multi-specialty robotics, conducted with Stryker and together with Dr. Tom Williamson, who's also on the call. Before I will introduce the project, I will give a bit of context. So I'll talk about what the Mako robotic system actually does. So in the picture, you can see that the Mako robotic system comprises of different things. So you can have the interface on the left, the guidance module, the actual arm that helps with the cutting. I'll explain that in more detail later. And it's classified as a semi-autonomous system. So it mostly operates on a predefined plan, and then it makes sure that the surgeon does not operate outside of that predefined plan. It's actually the most used robotic system for joint replacement surgeries worldwide, which include knee replacement, hip, shoulder, and also spine. So within a surgery, there are 4 main components where the Mako is actually actively being used. The first phase, we call phase 0, it's at the very start of the operation. So the patient will undergo a CT scan prior to the operation, and they will create a 3D modeling. And then based on that modeling, the surgeon can identify a specific plan specific to the patient, looking at the implant size and the positioning. So this is very valuable for the patient and the surgeon, basically making sure that they can cater to specific patient needs. And then the first phase in the surgery is the registration. So in the image, you can see the surgeon. The surgeon is the one holding the tool. We also blurred out some of the sensitive elements in the picture.
The blood.
Yeah, basically. And then you can also see a personal assistant of the surgeon, a scrub nurse, and then there's also a Mako product specialist, which is over at the console. That's not visible in this picture, but those are the main actors that we are looking at. So first, in this phase, the surgeon has to localize the robot and the patient within space. So they capture points on the bone to make sure that the Mako knows where the robot is and where the patient is. And then the second phase later on, after some prep, is the actual bone cutting. So then you can see with the red cover, the MVS moves the robotic arm into position close to the patient. And then the surgeon will cut within the predefined boundaries. It's hard to see, but basically there's a green border around the patient there. And that's the area on which the surgeon can operate. And then the green area, that means the area that needs to be removed. So the white behind that is the plant. And it can also go to red, which is a little bit over the plan, but not clinically significant. And then after the cuts and after the implant positioning, then the surgeon finally uses the Mako system to verify the accuracy of the cuts and the implant positioning, which is in the last part.
Okay, I'll give a quick introduction for the project. So this is the multi-specialty robotics project, looking at the Mako robot and looking to explore how the Mako could be used for multi-specialty use, so different types of procedures, mainly around arthroplasty. This is to do with optimizing the workflows of this robot to see how it could be used in repeated different operating theaters quite quickly, and to generally demonstrate a value and to increase adoption as well. Some of the key challenges from this were the fact that there are very few Mako systems in public hospitals. They're mostly private hospitals. The Mako is expensive, but hospitals need to see a return on that investment as well, and it does seem to be there. The robots are generally used for one procedure type only, and those procedures do vary between about, I think at the quickest, about 60 minutes up to about 90 minutes to 2 hours for typical knee or hip operations, that can really blow out for things like spinal fusion procedures, depending on the complexity of the surgery. It's not uncommon to get a spinal surgery that goes for 4 to 6 hours. The scope of this project was in arthroplasty, so joint replacement. So total knee, arthroplasty, partial knee, total hip, reverse shoulder, and spinal fusion. So the Mako currently does total knee, partial knee, total hip, and is very soon looking at doing reverse shoulder and spinal fusion as well. So why this matters? To increase the public access, increasing adoption across all hospitals will in turn maximize the efficiency of the actual robot. Being able to do it through a multi-specialty Mako and have better utilization will in turn demonstrate a lot of value for the hospital. So then you'll end up with financial operational benefits, and then in turn that will also drive growth for the company, for Stryker, and that means that they can invest more money into research and to further enhance the Mako system as well. A quick overview of how we approach this. This was a mixed method approach, predominantly looking at qualitative studies, so lots of interviews, and with a little bit of qualitative as well, which we'll show in a few later slides, generally tracking the timings of the phases of the operations. The big challenges that we identified, 3 overlapping areas, were workflows, the workflow of the actual operation, the role of the 3 main players that have contact with the Mako, which was the surgeon, the Mako product specialist, and also on occasions the scrub nurse or the theatre nurse, and the logistics between those people working together to have a successful operation. The data collection for us was mainly observations, surgical observations, review of publications, particularly around those surgeries which currently don't use the Mako, such as the spinal and reverse shoulder surgeries, and interviews with the Mako product specialists themselves, as they have the most contact with the Mako throughout surgeries and they know the system very well. The analysis focus, we looked at mapping the timelines of each procedure and identifying different barriers as well throughout each procedure. And in this study, we developed a few different tools. We'll talk about the TSI method. We've developed 2 other tools, which is the Observe tool and also modeling through Stryker as well, which is scheduling. We won't talk about that in this presentation, but we might talk about it in another presentation when the report gets released publicly. So publication review, this is what we came out with from some of the observations. We have a timeline which shows different phases, as Jasper highlighted earlier on. We look at preparing the Mako, and then there's a preoperative phase, which is mainly the preparation of the patient and the setting up and calibration. The Mako robot, as you can see with those kind of burnt orange boxes there, is used for a very small amount of time at the beginning to prepare itself, and then it's used for registration in the pre-op phase, and then the cutting of the bone happens, in which it's used a lot through intra-op phase, and then essentially the Mako is not used for the remainder of the surgery. So there's a 15 to 20 minute section in the middle of the surgery where it is used a lot, and then it's not used at all for the rest of the surgery.
That's a clarification question.
Yes.
So pre-op, they're still actually cutting the patient?
Yes.
All right.
Yes. The cutting happens at T = 0. If you look at the yellow line at the bottom there.
Yeah, okay.
So T = 0 is the actual incision, and the patient comes in, so the pre-op is still beforehand. Basically, pre-op is anything before the robot is used for cutting. Yeah. Average time for this, so this in particular is for knee surgery, so TKA, total knee arthroplasties. We also looked at the other 4 and developed timelines for those as well. And as you can see, the average time there, which is based on observation of training videos and also publications, was about 61 minutes, give or take 13 minutes or so. Sometimes that can be a lot longer. A lot of the observations that we saw were around that time as well. This research is based on a study out of Italy, out of the University of Modena, for Prati and others. And this was looking at how to gather resources, requirement gathering for user experience. So this is a way to kind of consolidate and to standardize user experience through different scenarios. The Prati researchers generally started about looking with tractor interactive panels and other automotive vehicles as well. And very quickly, this has been seen as a very good way to actually get a lot of early UX design requirement gathering for human-centered, human robot interaction and human robot collaboration as well. We have adapted this and we have adapted this for our own surgeries as well. I will move on and show, this is for Jasper to present.
Yes.
Okay, there it gets.
So as Mel mentioned, we had the method from Prati, but then we figured we need to adapt it to make it suitable for the surgical context. So this is what it looks like filled out, but I'll quickly go through it. So we identified once again the different phases. Then we identified the different tasks that we are interested in. We collected the times it took to complete this task. And then what we were particularly interested in per the task, who are the actors involved and how do they interact with each other. What you might notice is that we divided up the different elements of the Mako system. This, for instance, allowed us to see when the surgeon is actually looking at the screen or when it's looking at the patient. And then some of the other parts that we added are from the literature. So we looked at how have other people analyzed different robotic systems in the operation theater. And from that, we added workflow disruptions. So we're interested in what happens when there's a deviation from the standard workflow. How was this caused and how did they overcome it? And then we were also noting down what were the conditions of the workspace. So we fill it out. You might see that there are also some orange dots. This goes hand in hand with some of the limitations of the videos. So basically an orange dot means that we're pretty confident that the actor was involved, but we were just simply not able to see it in what the video was showing us. So while we were filling this out, on the other hand, we were using the qualitative software analysis of Atlas TI. So you can see once again that we have those different phases that we have identified and note down in the TSI here in the same way. Elle and I individually coded these and then we compared it for accuracy. And then additionally, what we are also interested in, because in these videos, the surgeons, they provide a sort of narration. So we also captured these quotations as they sometimes talk about how they interact with some of the other surgical members or how they perceive their interaction with the Mako system. And in a bit, I will talk about those findings, but first I will talk about some of the interviews that we conducted. So when we did the observations, it's of course us as researchers looking into what is happening, but we're also interested in how the actual actors within this system experience those different collaborations with the surgeon, with the Mako and other staff members. So therefore we sought out to interview some Mako product specialists. In total, we were able to interview 4 MPSs in 60-minute interviews. We used a semi-structured interview guide, which basically means that we identified some topics that we wanted to cover, but were mostly led by the experience of the participants. So we were interested in some of the workflow dynamics, the logistical issues, and some of the technical challenges. We analyzed this using a thematic analysis, and we used inductive coding, and from that we identified 3 themes. The manual optimization, so optimization more related to the humans within the system, optimization in terms of logistics, so more about the scheduling, and then some of the technical improvements to the Mako system.
Okay, so what this all means. From the findings, workflow findings were the common themes is that the learning curve of using the Mako really does impact the efficiency. Some of the surgeries were about half an hour longer for junior surgeons that had not had experience with the Mako before. That quickly improves with experience, about 20 surgeries to get up to speed, really. The precise calibration does increase the setup time. So that means that compared to traditional surgeries, like manual surgeries, it is longer to use the Mako, but the Mako cutting happens a lot quicker itself. So the surgeons have precise cutting accuracy, and they tend to make up some of that time that is lost in the calibration and registration of the patient in the surgery. Workflow challenges were setup delays and tool adjustments, such as adjusting the tool for cutting can cause interruptions, and communication gaps between the MPSs and the surgeons can also affect the efficiency, particularly with the surgeon might need to redo some of that registration or the calibration of the bone so that the camera and the Mako knows where that is in the surgical space. For individual procedures, we had, for the total knee, frequent tool changes were needed, sometimes needed, I should say, calibration adjustments mid-procedure. For the hip, it generally was longer preparation times because of the complex alignment needs of both the hip pelvis, the socket, and also the hip, the leg femur. For the partial knee, generally a faster workflow, but had longer setup times. Reverse shoulder, which was not a Mako surgery, but other types of surgery, it's quite challenging because of the precise bone positioning, and it's a very small workspace in this shoulder itself. It's a very complex compartment. And for spinal fusion, as I mentioned previously, is very complex surgeries, and they can vary greatly. So it requires a lot of coordination across different teams, but also the different tools that are needed. For logistical findings, there are scheduling constraints. Often with single Mako systems, they need careful planning. The demand does exceed the availability, and there's very limited flexibility across the different procedures. You can book a Mako in, it's generally first come, first served in the systems that we have spoken about with the MPSs. System movement challenges in order to get the Mako in and out of operating theatres. Moving the Mako system between an OR requires a lot of assistance. The module, the main cutting module, weighs quite a lot, about 300 kilos. And so you need some untrained staff or other people to help you move it. Generally, infection control policies in hospitals might restrict the movement of the Mako in and out of the OR, which will definitely limit system movement as well. For resource optimization, hospitals themselves might need additional units to support the growing demand, which is costly, and there will need to be changes to protocols and also training for other staff members within the OR to enhance the system movement efficiency. From the interview findings, the three main actors were the surgeon, MPS, and the scrub nurse. We found that the interactions between these were quite paramount to how the procedure went. So we have with the surgeon and the MPS, the surgeon depends on the MPS for the setup, the calibration, and the adjustments. Over time, the MPS generally anticipates the surgeon's needs, which leads to smoother workflows. Many surgeons do have preferred MPSs that they do like to work with, and they prefer to work with them for all of their surgeries. And they build up a level of trust between the two of them. For the MPSs and the scrub nurse, the MPS generally does guide the scrub nurse during the robot registration and between transitions of different phases. Delays can occur if the nurse is unfamiliar with the Mako system itself. And with team dynamics, you end up with a seamless coordination and trust between the surgeon, the MPS, and the scrub nurse over a few different surgeries. And that generally does reduce the workflow interruptions. They tend to know how each other work. And then you'll get varying levels of MPS involvement based on that as well. For conclusions and for the next steps, these are the take-home messages from our research. Effective teamwork is absolutely crucial. Strong collaboration and trust between the MPSs, the scrub nurses, and the surgeons do drive a much smoother operation. Technical challenges do actually remain. There is a lot of calibration and setup delays that can happen, and they continue to impact the workflow efficiency. They are infrequent, but they can happen. Training does matter. Improved training for the scrub nurses and the Mako for the Mako generally enhances the efficiency and reduces disruptions. The scrub nurses tend to be prepared for what's going to be happening next. Experience definitely counts, familiarity and consistency. With the experience of the Mako across different surgical teams, particularly between the surgeon and the MPS, does optimize that procedure flow. And for a focus beyond the actual technology of the Mako, despite the technical abilities, the major gains do actually lie in the operational improvements, such as team coordination and trust building between those members of the operation room. Future research, I think this is Jasper's.
Yeah, so finally, looking at teams, some of this work for my PhD. As you can see on the screen, I'm now working on analyzing total hip replacement videos. And then I will compare these with the knee. We've also gained the ethics approval to actually go to the hospitals and observe the surgeries in person, which is really great. And I continue to interview more MPSs to gain deeper insights into their experiences. So, are there any questions?